Alright, we want to take a look at solving linear inequalities in two variables right now. We're going to start by solving linear equations in two variables graphically. First example here, I want to know, for example, where does f of x equal g of x? Now, f of x is this function. It is a constant function. G of x is this function, a decreasing line. If I want to know where f of x is equal to g of x, what I'm looking for is a point of intersection. And this point of intersection happens to line up right where x is equal to 6. So I know I can find a solution here at 6. Or I'll just say where x equals 6. Similarly, if I want to know where does g of x equal h of x. H of x is this constant function. G of x, decreasing, I can find the point of intersection for those two, and that point corresponds with where the value of x is equal to 3. So we know the solution here must be 3, or we can write x equals 3. Now for our linear inequalities, things get a bit more interesting. We're looking at a statement f of x is less than g of x, which is less than or equal to h of x. Another good way to think about this is, when is g of x, that decreasing line, in between our function f of x and our function g of x? H of x. So g of x is the decreasing line. Looks like it is bounded in between the two functions in this central area between the first point of intersection of g and h and the second point of intersection of f and h. Well, looking at the entire region in between, our solution set here will be an inequality. We can say x takes on a value such that it is between, x is greater than 2 but less than 4, greater than 3 but less than 6. Very often we treat this as in between rather than breaking it up into two inequalities, but the fact is, along the line, all these values are greater than 3. All these other values are less than 6, and notice our inequalities must match up, correspond with the original inequality. If we use interval notation, our values of x begin at 3 and go to 6. At 3, we do not have equality. We strictly have the inequality. This is where, remember, we will have our parentheses denoting that it is not equal there. At the value where x equals 6, we do have equality because it is less than or equal to. So in our interval notation, we will have a solid bracket instead. So we have our set builder notation or our interval notation. Now for this last inequality, I want to know, when is g of x greater than h of x? Well, keep in mind these are function values. For g of x to be greater than h of x, we want to look at where the g of x values are above as opposed to in between. When is g of x above h of x? Well, g of x is above h of x from the beginning of our graph. Keep in mind, though, our graph did not go to infinity in both directions. In fact, we started at a value where x was 0. So for our inequality, we have values of x. The values of x start at 0. And they stop when x is equal to 3. This was not equality, it was strictly greater than. So our inequality does not have the equal to symbols. X is simply a value between 0 and 3. We can write this also in interval notation. X value started at 0, increased until 3. We did not have equality at 0, so we will have our parenthesis. We also did not have equality at 3. We will also have a parenthesis there for our interval notation. So these values, strictly between 0 and 3, are the ones that cause g of x to be greater than h of x. And we're done.